S. Chan presents educational video lectures as per the new UGC CBCS curriculum. Absolutely free. Difficult science concepts made easy. Study anywhere, anytime.
Hello. Let's begin today's video with a quick question. How does organic chemistry relate the following objects? I have a common wood ant, our favorite lemons, a bottle of vinegar, and a common medicine taken by many heart patients, aspirin. Think about it, and I'll come back and reveal the answer. I am Dr. Sujata Sengupta, and welcome to the S. Chand Academy. If you want to learn more about today's lesson, then please refer to the book by S. Chand Publishing, link to which is provided in the drop box below. So with that, let's begin today's lesson. So I'd left you with a question. How did organic chemistry relate all of these following objects? Well, as you can see, the answer is carboxylic acids. Our common wood ant secretes formic acid, one of the simplest carboxylic acid that exists. The sourness of lemons, where does it come from? It comes from carboxylic acids. Acids like citric acid and malic acid. Our common vinegar that we commonly use for cooking, what does it consist of? Again, a carboxylic acid, acetic acid. And finally, aspirin, the medicine commonly prescribed to heart patients. What is it? Again, it's an example of a carboxylic acid known as acetyl salicylic acid. So, in today's lecture, we're going to be learning all about the chemistry of these molecules known as carboxylic acids. So, what are carboxylic acids? Basically, a carboxyl group will consist of the carbonyl group and a hydroxyl group attached to the same carbon atom. The carboxylic acid group is also commonly written as COOH. Molecules which contain this carboxyl group are commonly acidic in nature, and therefore they are referred to as a carboxylic acid. Formic acid, which was secreted by the ants, this is the simplest carboxylic acid, where the R group is nothing but a hydrogen. And we can classify our carboxylic acids as either being aliphatic or aromatic in nature. How? Depending upon the nature of this R or substituent groups. If the R is an alkyl group or a hydrogen, then they are known as our aliphatic acids. If it is an aromatic group attached to the carboxyl group, then these are known as our aromatic carboxylic acids. The simplest one, for example, is benzoic acid. So now comes the question, how do we name these acids? So we can have a trivial name and we can also have the IUPAC nomenclature. Let's start with the common or the trivial names. Several of the aliphatic carboxylic acids, they have been known for centuries. And so they are commonly known by their common or trivial names. For example, formic acid, it comes from the Latin word formica, which means ants. Acetic acid, which is found in vinegar, comes from the Latin word acetum. What does it mean? Sour. And if we have a substituent group present in our acid, then they are designated by Greek alphabets. So here we have our 4-carbon carboxylic acid, butyric acid, with, you can see, an amino substituent. How is this named? Like I said, we use the Greek alphabets. This is our alpha carbon, beta carbon, and our gamma carbon. So this molecule here is our gamma amino butyric acid. Moving on, let's look at the IUPAC nomenclature. So, in the IUPAC nomenclature, we will use the name of the alkane that corresponds to the longest continuous chain of carbon atoms. We will remove the E in the alkane and we replace it with the suffix oic acid. And the chain is always numbered with the carboxyl carbon. If you remember, when we name our molecules in the IUPAC nomenclature, the carboxylic acid group always gets the first priority. So here you can see I have ethanoic acid coming from the parent alkane ethane, and here I will have 4-amino-butanoic acid. Our previous example, the common name was gamma-aminobutyric acid, but in the IUPAC nomenclature, we can now number it 1, 2, 3, 4. The fourth carbon contains an amino group, and so the molecule is now known as 4-amino-butanoic acid. Certain aromatic carboxylic acids are going to be named as derivatives of benzoic acid. Benzoic acid being the simplest aromatic carboxylic acids. And when naming them, we will use ortho, meta and para to name the various substituents. So here I have para-aminobenzoic acid. The amino group is at the para position with respect to the carboxylic acid. And here I have ortho-hydroxybenzoic acid, which also has a common name many of you will know as salicylic acid. Next, let's look at another class of acids which are known as dicarboxylic acids. I'm sure many of you must have come across dicarboxylic acids in your organic laboratory. What are dicarboxylic acids? Well, dicarboxylic acids are compounds, as the name suggests, with 2 carboxyl groups. Usually, they can have in IUPAC nomenclature, but usually they are most commonly known by their trivial or common names. For example, here we have oxalic acid, succinic acid, malonic acid being some of the most common dicarboxylic acids. Let's look at some of the physical property of these carboxylic acid molecules. Carboxylic acid molecules are planar in nature with a planar carbonyl atom. They boil at much higher temperatures compared to aldehydes, ketones or alcohols having the same molecular weight. Why is that? Yes, that is due to the formation of a stable hydrogen bonded dimer. Now generally the carboxylic acids which have more than 8 carbon atoms tend to be solid in nature, and the melting points of a dicarboxylic acids are unusually very high. Why? Yes, because with 2 carboxyl groups they have a much greater hydrogen bonding effect. Our carboxylic acids also form hydrogen bonds with water, and so they tend to be miscible with water. They are extremely soluble in alcohol. Why? Because the acids form hydrogen bonds with our alcohols. Now we come to the most important property of our carboxylic acids, the reason we call them as acids. A carboxylic acid, it dissociates in water to give a proton and a carboxylate ion. This reaction is an equilibrium reaction which is designated by an equilibrium constant Ka, which is known as the acid dissociation constant. Generally or typically, we denote this acid dissociation constant as with a pKa value. All right, what is pKa? You will remember pKa is nothing but the negative log of this acid dissociation constant. This pKa value will determine the strength of the dissociation of the acid or the relative acidic strength of the acid. Carboxylic acids tend to have a pKa of 5. If you remember, in our previous video in this S. Chand Academy, we had discussed about the chemistry of alcohols. Alcohols too would dissociate and it would form an alkoxide ion and a proton. But the alcohols, being acidic, however, they are weakly acidic. Their pKa values of 16. Remember, lower the pKa value, the stronger is its acidic strength. So why this difference? Why are carboxylic acids more stronger acids than alcohols? Well, look at the structure of the carboxylate ion. Here you can see that upon dissociation, once the acid forms the carboxylate ion, this carboxylate ion is resonance stabilized. This negative charge, you can see, it gets delocalized through resonance stabilization over 2 oxygen atoms, leading to a greater stability of the carboxylate ion. This is not possible in the case of the alkoxide ions. And therefore, our carboxylic acids are much more acidic in nature compared to that of our alcohols. Now, what do you think would affect the acidity of the acid? You are right. It depends upon the stability of the carboxylate ion. Any substituent which stabilizes our negatively charged carboxylate ion is going to promote the dissociation and therefore results in a much stronger acid. So, let's look at chloroacetic acid. Chloroacetic acid has one chlorine atom substituting one of the hydrogens of acetic acid. What's so special about this chlorine? What does it do? You know, you have guessed it, the chlorine atom is highly electronegative in nature. What does that mean? It withdraws the electron density towards itself, and therefore it increases the stability of the resulting carboxylate ion. As a result, our chloroacetic acid, therefore, with a much more stable resulting carboxylate ion, has a pKa of 2.86, much more acidic than our simple acetic acid molecule. And if you consider trichloroacetic acid, here we have 3 chlorine atoms attached to the alpha carbon. So the effect of the 3 chlorine atoms is so strong, it increases the stability of the carboxylate ion so much that our trichloroacetic acid is as strong as most mineral acids. Similar factors will also affect the acidity of our aromatic acids. So, for example, electron withdrawing groups will again stabilize the resulting carboxylate ion, and therefore para-nitrobenzoic acid is going to be a much stronger acid, whereas electron donating groups like a methoxy group would destabilize the carboxylate ion, making the molecule less acidic in nature. And always remember that these effects are always going to be the most at the ortho and our para positions. Now that we have covered its properties, let me leave you with a quick question before we take a break. How do we prepare our carboxylic acids? If you have been following all our videos in this S. Chand Academy, I am sure you would be able to think of a few common methods for its preparation.
Hi, I'm Manika and you're watching S. Chand Academy. I'll be discussing the topics like carbohydrates, amino acids, peptides, proteins and many other topics related to BSc program. For more such lecture, you can stay tuned to our channel and subscribe to our videos so that you get more and more info about our upcoming lectures. You can also refer to our previous lectures on the related topics. Stay tuned, stay focused, because it may help you in your competitive exams also and preparation of the other topics also related to your courses. Thank you.
Welcome back to the S. Chand Academy. Before our break, I had left you with the question. What are some of the methods do you think that we can use to prepare carboxylic acids? I'm sure you have been following our previous videos and you can name some of the common methods. So let's quickly revise and take a look. The most common method, I hope you have guessed it correctly, to prepare our carboxylic acids is by the oxidation of our primary alcohols and aldehydes by chromic acids. So, primary alcohols on oxidation with chromic acid, PDC or even potassium permanganate gives you our carboxylic acids. These carboxylic acids can also be prepared from the alkenes. Remember, when alkenes are treated with a cold dilute potassium permanganate solution, they give us what is known as glycols. However, that same alkenes, if they are treated with a concentrated potassium permanganate solution, then the glycols get oxidized to our carboxylic acids. Alkynes are also a source of carboxylic acids. How? If you remember that either by ozonolysis followed by hydrolysis or with vigorous potassium permanganate oxidation conditions, then the alkynes cleave and they give us our carboxylic acids. Remember, this was an excellent method by which we can also determine the position of the alkyne group in a molecule. Finally, Grignard's reagent are organomagnesium halides. These add to carbon dioxide followed by hydrolysis to give us the carboxylic acids. These Grignard's reagent, how do we get them? Yes, these in turn are going to come from our alkyl halides. And so, this method serves as an excellent way to convert our alkyl halides into carboxylic acids. Finally, one of the most important ways to synthesize the carboxylic acids is by the hydrolysis of acid derivatives. So, acid derivatives like esters on hydrolysis, either in an acidic or a basic condition, it gives us the carboxylic acids. The acid catalyzed hydrolysis of our esters is an equilibrium reaction and it is opposite to that of the Fischer esterification. The basic hydrolysis of esters to give carboxylic acids is commonly known as saponification. This is a very popular method and it is very routinely or commonly done in the undergraduate laboratories. So, when ethyl benzoate is treated with an aqueous solution of sodium hydroxide, it undergoes hydrolysis to give us the sodium salt of the corresponding carboxylic acid, sodium benzoate, and our alcohol, ethyl alcohol. Let's look at this reaction a little more. So, in our first step, our nucleophile or our base, sodium hydroxide, the hydroxyl it attacks the electrophilic carbon of our ester molecule and it forms our tetrahedral intermediate. As soon as this is formed, now we will have a loss of our ethoxy group followed by the reformation of the carbonyl moiety. Now, a very fast proton transfer takes place to give us the sodium salt of benzoic acid. And our alcohol, ethyl alcohol, is produced. Now that we have our sodium salt of benzoic acid, a simple final step by treating this with an acid gives us our benzoic acid molecule. So, here we had the basic hydrolysis of ethyl benzoate, ultimately giving us benzoic acid. Before we move on, let's quickly look at the saponification reaction. In Latin, the word saponis, it means soap, and so the term saponification literally means making of soaps. How do we make soaps? Well, generally a basic hydrolysis of fats or oils, or commonly known as triglycerides, gives us soaps. Triglycerides are nothing but ester molecules. They are esters of long chain carboxylic acids with the triol glycerol. And so, when sodium hydroxide is treated with the fat or the triglyceride, it hydrolyzes the fat to produce the sodium salt of the long chain carboxylic acids, our soap, along with the byproduct glycerol. This was our saponification reaction. Now, let's look at some of the reactions of our carboxylic acids. If you noticed, our carboxylic acids they contain a carbonyl group very similar to ketones and aldehydes. Aldehydes and ketones, if you remember, they tend to undergo a nucleophilic addition reaction to this carbonyl group. The carboxylic acids and their derivatives, they react by what is known as a nucleophilic acyl substitution, where one nucleophile will substitute the another nucleophile present in the acyl group. Now, when I said carboxylic acid derivatives, what did I mean? These will include molecules like acyl halides, anhydrides, esters and amides. Nucleophilic acyl substitution is the most common method for interconverting among the acids and the acid derivatives. Stay tuned to our other videos on the chemistry of carboxylic acid derivatives to know more about this reaction. Just a couple of more reactions which are important. The first is if we want to convert our carboxylic acids more specifically to our methyl esters. How is that achieved? The carboxylic acids can readily be converted to the methyl ester by simply treating our acid with an ethereal solution of diazomethane. We end up getting our methyl esters with the evolution of nitrogen gas. Any excess of diazomethane that we had, it evaporates off. As a result, our methyl esters can be very easily isolated. All we need to do is evaporate off the solvent, and the yields are nearly quantitative in nature. Our carboxylic acids can also be reduced to the primary alcohols. How does that take place? Yes, with the help of hydride reducing agents like lithium aluminum hydride. So, a lithium aluminum hydride, it reduces our carboxylic acids to the primary alcohols. Finally, we have what is known as an HVZ or a Hell-Vollard-Zielinski reaction. What happens here? Here it's an organic reaction where we can convert our carboxylic acids into an alpha halocarboxylic acid. It's an example of a substitution reaction where one of the alpha hydrogens can easily be substituted with a halogen atom. So for this reaction, it occurs in the presence of phosphorus as our catalyst along with our halogen gas and finally hydrolysis with water. In a typical reaction condition, the red phosphorus and bromine, they are treated with the carboxylic acid followed by hydrolysis to give us our alpha halocarboxylic acids. So with that, we come to the end of today's lecture. We had discussed about the chemistry of carboxylic acids. We looked at some of the examples of carboxylic acids found in nature, its nomenclature, properties, methods of preparation and some of the reaction. If you want to know more about the chemistry of carboxylic acids, you can always refer to the book by S. Chand Publishing, link to which is provided in the drop box below. I hope you have enjoyed our video, you have learnt a lot. Please hit the like, share and subscribe button and don't forget to click on the bell icon so that you can always stay tuned for our further videos.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.